Hello everyone, Jai Hind. So I'm going to discuss equivalence among regular expression, finite automata and regular grammar. You will see that by this equivalence what we mean that regular expression and finite automata and regular grammar. All these three things are connected. So I have seen in my previous lecture, you have seen it that regular expression can be converted into finite automata. Now we will see that finite automata can also be converted into regular expression. That means given finite automata, how to get regular expression. Same thing from regular finite automata to regular grammar and from regular grammar to finite automata. And we can see that this regular expression and this also, all these three things are interconnected, right? So we are going to discuss about this connection, that how we are done we already that regular expression to finite automata. So first I'm going to discuss about finite automata to regular expression. Then we'll discuss how to connect regular finite automata and regular grammar, hence regular expression to regular grammar. So this is the talk. So finite automata to regular expression. So we have many methods. But I'm going to discuss on only Arden's theorem. So what is Arden's theorem? So you know this Arden's theorem is based on the regular expressions identity. So if it is saying that if R is a regular expression and if this can be written as R is T plus Rs, right? If R is a regular expression which can be written as T plus Rs, where T is any regular expression, R is the same thing, and S is not equal to lambda. This should not be empty. This is the restriction on S, right? So if you can write this, then R from this right hand side can be eliminated. So then R equal to Ts star. This is very, very important result, that if R is equal to T plus Rs, then R can be written as Ts star, right? This R from the right hand side can be eliminated. If you are applying this Arden's theorem, make sure that S is not empty. This should not be empty. At least this is lambda, right? So if it is empty, this Arden's theorem is not going to be applicable. So this is the Arden's theorem. Actually, this Arden's theorem has a limitation. In this one, the first limitation is that the transition graph does not have any lambda mu. So what do you mean by this transition graph? It has no lambda mu. If it has lambda mu, that means you have to remove the lambda transitions, right? Then only you can apply the Arden's theorem. And it can be applied on NFA, but only it has problem with the lambda mu. So if NFA has lambda mu, you have to remove the lambda transitions. Second thing, it has only one initial state. It can have many final state, but initial state is limited to one. So what are these? And sometimes we call it this algebraic method also, right? So sometimes this Arden's theorem is also called as algebraic method to convert regular finite automata to regular expressions. So this is actually right. In this method, we write n equations. So if you have three states, you have to write three equations. So how to write the equations? Suppose Q1, Q2 are numbered as states. So in this one, Q1 will be written as Q1 alpha 11. Alpha 11 is transition going from 1 to 1. Sometimes we call it regular expressions also. So alpha 11 means 1 to 1, right? Going from state 1 to state 2, 1. Same thing plus Q2. It is actually linear combination of all the state Q2 alpha 2 1, because destination is 1, here source is 1, so everybody will lead to 1. So alpha 2 1, right? Same plus Q3 alpha 3 1, 3 2 1, right? in general, if you have n states, so qn alpha n1 plus lambda, where if you have starting state as q1, lambda is going to be added. This is the q1. Same thing if you write q2, q2 is q1 alpha 1 2. You know, we are interested in going to 2, so you will be writing 1 2 2, alpha 1 2 2, right? And then q2 alpha 2 2, then you will write q2 alpha 2 2. So you see, we are interested in going to 2, so alpha 2 2 plus q3 alpha 3 2. You are going to from 3 to 2. So up to and so on, there is no addition of lambda in this q2 transition. So same thing, if you are interested in q3, how to write? q3 will be q1, you will start with q1 alpha 1 3. You know, we are interested in going to 3 plus q2 alpha 2 to 3. This is 3, right? And q3 alpha 3 3 up to and so on. If you are interested in qn alpha n3, everybody will go to 3. So this is the algebraic method. You have to design like this, and then suppose you have many like q any one final state. Let's say out of this you have q3 final state, so we are going to solve for q3 only. If you have q1 and q2 two final state, you are going to solve for q1 and q2. So let's understand this method. You see here already, as we know that what is its answer. If you just understand its answer, this is 0 plus 1 star and 0 1. So that we know that its regular expression is 0 plus 1 star 0 1. So how to write it? You see here, q1 is q1, right, alpha 1 1, alpha 1 1, 1 to 1 is 0 plus 1, 1 to 1 is 0 plus 1 plus q2 alpha 2 1. There is no transition from 2 to 1. So this become 5 plus q3, you have 3 state, q3 alpha 3 1, there is no transition from 3 to 1, this is 5. Since q1 is starting state, so we will add lambda. This is q1 equation. So this can be simplified to q1 is q1 0 plus 1 plus lambda, plus lambda. Yeah. So this is equation number 1, right? Yes. So same thing, let's write for q2. If you write for q2, q2 is q1 alpha 1 2, alpha 1 2, 1 to 2 is 0, 1 to 2 is 0 plus q2 alpha 2 2, there is no 2 2, so this is 5 plus q3 alpha 3 2, 3 2, there is nothing, so this is 5. So if you just simplify this, q2 is q1 0, this is your equation number 2, right? So now if you just go to q3, right, so q3 is q1 alpha 1 3, there is no transition from 1 3, so this become 5 plus q2 alpha 2 3, there is transition from 2 to 3, this is 1 plus q3 alpha 3 3, there is no transition from 3 to 3, this is 5. So now by this one, q3 is q2 1. So this is equation number 3. So equation number 1, equation number 2 and equation number 3, right? So since now q3 is the only final state, so we are going to solve only q3 equation. So in order to get q3, you have to solve q2. q2 is q1 0. In order to get q2, right, look at here. Since q3 is the final state, you will start from q3 equal to q2 1. Yes. Now go to q2. q2 is q1 0. That means in order to get q2, you have to get q1. So it's better to go and solve q1. So q1 is here. q1 is q1 0 plus 1 plus lambda. And if you just see the Arden's theorem is saying that T plus Rs R equal to Rs plus T is the same thing. There is no problem, right? Because plus is commutative over here. So by this method, R is Ts star. So T here is lambda and R is same thing here. R is here, and S is here. So by this method, RQ1 is Ts star. Lambda and S star means 0 plus 1 star. So by this method, Q1 will be 0 plus 1 star. So we got the Q1. And once you get the Q1, you can apply it over here to get Q2. So by this method, Q2 is Q1 0. And you got Q1 0 plus 1 star, 0 plus 1 star, Q1 0. So this is Q2. Just apply Q2 here. So you will see that this Q2 0 plus 1 star and 0 and then 1. This is your Q3. So since Q3 is the only final state, so final regular expression is given by 0 plus 1 star 0 1, which is the same over here. Look at here. It's the same answer, 0 plus 1 star 0 1. So that means this method is correct. So, you know, right? So this is first example. Let's have another example. You can see here. We have 4 states over here. So if you start by writing this, you will see that let's write it, right? So Q1 is Q1, 4 equations you need to get. 4 equations since we have 4 states, right? But since Q1 is the only final state, you have to solve only for Q1. So Q1 is Q1 alpha 1 1, nothing. There is no transition from 1 to 1 plus Q2 alpha 2 1, 2 to 1, 2 to 1 is B. Q2B plus Q3 alpha 3 1, yes. 3 to 1 is A plus Q4 alpha 4 1. There is no transition from 4 to 1. So Q4 phi plus lambda. So if you just simplify this Q1 equation, you will see Q2B plus Q3A plus lambda, calling equation 1. This is the same here, Q2B plus Q3A plus lambda. This is Q1 equation. Similarly, if you talk about Q2, Q1 alpha 1 2. 1 to 2 is A plus Q2 alpha 2 2 is nothing plus Q3 alpha 3 2 3 2 3 to 2 is nothing, right? Plus Q4 alpha 4 2 4 2 4 2 is 4 to 2 is nothing, right? So this Q2 will be Q1A only. This is equation number 2, which is correct here, right? So similarly, if you just talk about Q3, Q1 alpha 1 3, 1 2 3, yes, 1 2 3 is B plus Q2 alpha 2 2 3. 2 to 3 is nothing plus Q3 alpha 3 3. 3 to 3 is nothing plus Q4 alpha 4 3. Is there any transition from 4 to 3? 4 to 4. 4 to 4 is A plus B. So this will be 4 to 3 is nothing. 4 to 3 is nothing. So this is 5. So this will be Q1B. This is Q3. So if you just go to Q4, you will see that Q1 alpha 1 1 1 4. 1 to 4 there is no transition plus Q2 alpha 2 to 4 there is transition. You know, all the transition will be covered. Q3 alpha 3 to 4. 3 to 4 is B plus Q4 alpha 4 to 4. 4 to 4 is either A or B, right? So this Q1 will be Q2A plus Q3B plus Q4 A plus B. This is equation number 4. So this is equation number 3, this is 2, this is 1, right? So and now time is to solve the equations, right? So after writing all these equations 1, 2 and 3 and 4, we know that only Q1 is the final. So we need to solve only Q1. In order to solve Q1, you see here you have to get Q2 and you have to get Q3, right? So Q2 is here Q1A, right? So Q2 is here Q1A. So that Q2 you can replace this Q2 here to get Q1 equal to Q1AB. Q2 is Q1AB plus Q3A plus lambda, right? And now Q3 is A is also Q1B, right? So if you just go here and write here, so Q3 is also, so now Q1 will be Q1AB plus Q3. Q3 is Q1B. Q1 BA plus lambda. Now Q1 can be outside. Q1 AB plus BA plus lambda, right? So this is Q1. So this is simple that Arden's theorem can be applied. R is, this is T and this is R and this is S. So by Arden's theorem, Q1 will be TS star lambda AB plus BA star, right? So Q1 will be equal to AB plus BA whole star. And since Q1 is the final state, this is the regular expression. So this is very easy method to get the regular expressions, right? Yeah. So this is another example you can see here. Same thing, I am writing Q1 and then Q2. You have 3 states, Q1, Q2 and Q3. By the same method, you can write Q1, Q2, Q3. And then you can see here this Arden's theorem can directly be applied over here. So Q1 will be 0 star. And once Q1 is here, so you can change the Q2 because Q1 becomes 0 star. Q2 is 0 star 1 plus Q2 1. It's very simple. Now this is T and this is R, this is S. So Q2 will be TS star 0 star 1 and then 1 star. This is Q2. So since Q2 is final state, you have to solve Q2 and Q1 is already 0 star. Q2 is here 0 star 1 star. So you just add them together because no need to solve the Q3 because Q3 is not a final state, right? So Q1 is 0 star, Q2 is this. So overall regular expression will be given by addition of this 0, 1, 1 star. That is it. This is the simple answer, right? So yes, Q1 plus Q2, and since this can be further simplified by taking 0 star outside, 1 plus lambda plus 1, 1 star, and you know that lambda plus RR star equal to R star. So actually this become 1 star and then 0 star is already there. So this identity is very, very important. So answer is 0 star 1 star. So another conversion is like remaining, which is regular grammar and regular expression. Of course, regular grammar are finite automata. And we know that a grammar V sigma SP is said to be regular if and only if each production rule is of this form. A goes to small ab or small a, where small a is from the terminal alphabet and A and B are the non-terminal. So regular grammar is very simple. It is actually the grammar type 3 grammar. Sometimes we call it type 3 grammar. Non-terminal derived terminal followed by non-terminal or single terminal. So now regular expression can be converted into regular grammar by using the following steps, right? Yeah. Draw an NFA for the regular expression. Convert into DFA. If you want to convert into DFA, it is easy. After then use construction, following construction to convert DFA to regular grammar. Let's have one example. Yeah. So you see here, this is the 0, this is your regular expression, 0 plus 1 star. This is the regular expression which we did just now, 0 plus 1 star 0 1. You can draw its finite automata. So once you draw its finite automata, this is the finite automata, right? So what construction is saying? Construction is very simple, right? So since this is finite automata, if you just understand, M is Q sigma delta Q0 and F. This is your machine. This is the machine. Now, in order to get grammar from this, what is grammar tuple? V sigma S and P. Here, non-terminal you need. So, non-terminal is just like all these states written in capital letter. So, you get it V. In this non-terminal, write all these states only in capital letter. There is no change in sigma. We don't require delta in the grammar, right? We need starting state correspond to Q0, right? This production rule is basically defined by this lambda. Production rule is going to be defined by this transition rule. How? Look at here. Q1, yes, you will write capital. Q1 goes to, you hear 0, 0, take 0, your destination is Q1. So this is one production rule which is regular. Then again 1, still you are going to Q1, this is 1 Q1, and this one is still you are going to Q2, 0 Q2. Remember, if destination where you are reaching is not a final, so no problem. You just write down these rules, right? So we are done with Q1 production, Q1 rule. What about Q2? If you look at here, Q2 goes to 1 Q3, but you remember Q3 is also a final state. So just write down 1 only, no state attachment, right? So this Q2 is having 1 Q3, and since destination is final, so just add 1 also. There is no transition from Q3, so leave as it is. So how to check whether this grammar is accepting the same thing as this finite automata? Look at here. What is minimum language accepted by this finite automata is 0, 1. Yes. So what is minimum language accepted by this grammar? You will start from Q1. If you start from Q1, right? Yes. Starting state Q1. You can go to 0 Q2, right? Yes, 0 Q2. You can go to 0 Q2, and then Q2 can go to 1. So 0 and 1. So that is you are getting 0, 1 minimum, right? So let's see if whether it is accepting the W equal to 0, 0, 1 or not. Yes, it can go. Start from Q1. 0, 0, 1. So 0 Q1. You can take 0 Q1, right? Yes. And again you can go to 0 Q1 is replaced by 0 Q2. Yes. And then Q2 can go to 1. So Q2 can go to 1. So this is accepting the 0, 0, 1. Definitely 0, 0, 1 is also accepted. So this grammar is the same equivalence of the finite automata. So let me again conclude that if somebody is saying how to convert a regular expression into the corresponding grammar, what you should do, find out NFA of this grammar, right? After finding out, apply this construction. No need of converting into DFA. This can serve the purpose, right? Only remember that if source Q1, 0 Q2, check. If Q2 is not a final state, there is no problem. If destination is final state, you have to add the simple transition without changing the transition, right? So let's have like only one limitation with this kind of finite automata. Had it been if this is starting state is also a final, right? Suppose starting state is final. So what you need to add again, you have to add like Q1 destination, so 0 is also added, right, and one is also added, and epsilon will also be added, right, because this is also accepting the epsilon transition. So if your starting state is also a final, you have to add q1 to epsilon also. So this is the only limitation. If your starting is not final, there is no problem, right? So this limitation is the most important limitation. So next one is how to convert regular grammar to finite automata. This is regular grammar. If you are converting regular grammar to finite automata, you will get the non-deterministic. You will never get the deterministic. For example, this is a grammar, regular grammar, right? So apply the same construction, reverse it, right? So like see here, yes, you have three non-terminal A and B, right? In this regular grammar to finite automata, you have to add another non-terminal which is not present here and make that non-terminal as a final state, right? This is starting, reverse the construction, S goes to small a s, right here, and then BA, right here BA, same construction I am reversing, and then S goes to B, right? That means if you see here, it is clear, but if you are checking S goes to B like this, this will go to the final, right? This kind of transition where only you are getting terminal in the right, they will lead to the final state. A goes to BB, yes, A goes to BB, no problem. B goes to B. So this will be going to here, and there is no transition from the final state. You will see that this will be an FA, and if somebody is asking to convert into DFA, you have to convert into DFA to get the corresponding DFA from a particular grammar. So this is very easy. Remember that if you are converting regular grammar to finite automata, you will get NFA, you will not get DFA. And remember this kind of state, S to B, where only you are getting terminal, all will lead to the final state, which is not currently in the list. So these are the references, right? You can follow them, John Hopcroft and KLP Misra and Peter Lynch. And thank you very much.